we can start. Let's welcome our next speaker, Jan Lang or Jen Lang.
Whatever. Okay, thank you very much for introduction. Now I'm going to place a copy of my slides on chat. Yes, you should get in your chat a copy of my slides. Yes, which means in the case that I will be too fast or too slow, you can look forward or look in the back. Yes. Now, okay, did you get the chat? I think that yes. Now let me start sharing my screen. Okay, share the screen, perfect. Now here should be my screen, and let me look here full screen. Okay, perfect. Come on, okay. Now, can you see my screen?
Yes.
Perfect. Now, please, one thing in this talk, if you have any question, any comments, do not hesitate, switch on your mic, shout at me and stop me, yes? Okay, don't hesitate. Now, what I'm going to be talking today, it's slightly different from the previous talk, yes? I will be talking about much more simple concept and much more simple stuff. The focus of this talk is going to be about Sobolev embedding, and I will be mainly focusing on the situation when the Sobolev embedding is non-compact, yes? We knew there is a plenty of literature which is study a quality of compactness of Sobolev embedding, because we all knew that when the Sobolev embedding is compact, it's related to some behavior of eigenfunction for some problems, yes. But I will just look for the case when the Sobolev embedding is non-compact, yes. But before I will really dive into my talk, I would like to really thank organizer for organizing such splendid lectures and so many interesting talks. And I would like to highly recommend them to do much more similar talks, because we which are fortunate, which are living in much more peaceful world, we be happy to share and support Ukrainian mathematical community. Okay, let me start. At first, let us try to start with some introductions and definition, yes? Here, if we have some bounded linear map, which is mapping one Banach space into another Banach space, I would like to study a quality of compactness of such embedding and non-compactness, yes? For the future, by Bx, I will understand a unit ball in the space X. Now, if I want to measure a quality of compactness or perhaps non-compactness, quite important tool, it's something which is called entropy numbers. Entropy numbers. Entropy numbers are quantities which are defined by the following way. You will go take an image of unit ball in your mapping T. You will get some object in your target space Y. That object is, of course, going to be bounded and convex set. And now our task is going to be try to cover the image of unit ball by number of balls. In this case, I would like to find what is the smallest possible radius which can guarantee that I'm covering the image of unit ball by 2 to the power k minus 1 balls. Yes, this quantity, it's called kth entropy number. One thing is obvious: if the embedding T is compact, then with the covering by more and more balls, radius which you need to for covering that image of unit ball will decrease to 0. Now, another quantity which is quite often used for describing quality of compactness, it's something which is called S numbers or N width, yes. It depends which school are you using. If you are using the school around with people from Germany, from Jena, you will perhaps using notation of S width. If you are closer to Kolmogorov approach, you will be calling this object N width, yes. And there are different quantities which are used to measure a quality of compactness of our set. One quantity, it's called approximation numbers. By we understand just what. We will just going to take a map T, and we would like try to approximate that map T by some operators with the rank at most n or n minus 1, yes? Which means you are looking for distance of your map T from all linear operators with the rank less than n, yes? This is going to be called an approximation number. Another quantity which is used, it's called Kolmogorov number. Roughly speaking, Kolmogorov number will do what? You will take image of unit balls, what I mentioned before. This is going to give you a bounded convex set in your space Y, and you would like to go and try to approximate this set by some n-dimensional subspace. You will get, and you look among all n-dimensional subspaces, and you will look for the best approximation. That is going to be n Kolmogorov number. And then there are much more numbers, like a Gelfand number. In this case, you are going to do approximation by spaces with the not dimension n, but with the codimension n. Then is something else like a Bernstein number. The Bernstein number is in some sense quite interesting. Why? Here is the definition of the Bernstein number. If you look at this definition of the Bernstein number, it's a little bit difficult to digest, but roughly what is the meaning of that is the following. You will look, oh, there should be X here. You will look for the image of a unit ball X in your target space. You are looking for the image of unit ball Bx by mapping T, and you would like to see what is the largest n-dimensional ball which you can squeeze in. And that is going to be calling nth Bernstein number, yes? And there are some another definition like isomorphism numbers, yes? There is much more quantities which are used to approximate or estimate quality of your mapping, yes? Here you have a Mitagin numbers, or Mitagin, Boris Mitagin, it's my colleague from the Ohio State, Wells numbers, Chang number, Hilbert numbers, yes? All these numbers are just going to tell you how well its image of your operator approximate by some n-dimensional structures, yes? For all those S numbers, we knew that always first S numbers is equal to the norm of operator, and then those other numbers are going to 0. Among those S numbers, there are some relations, yes? Bit, of course, and there are some another properties, which I'm not going to mention here. Now, all those S numbers are related by the following way. Approximation numbers are the largest one, then follow with Kolmogorov and Gelfand as numbers, and then Bernstein, Mitagin numbers, isomorphism, Hilbert numbers, and so on, yes. Also, all these numbers are having some beautiful duality mapping, yes. But the most important thing which we have here is the following observation. When our map T is compact, when T is compact, that is going to happen if and only if entropy numbers are going to go to 0, and also if Kolmogorov numbers are going to 0, yes. These are nice conditions which can give us, which is going to tell us when the mapping is compact or is, if it's, and when it's non-compact. Now also these quantities, these entropy numbers and their limit, it's used for measuring a quality of non-compactness, which means I'm going to say that limit of those entropy numbers, which I'm labeling like beta T, yes, limit of entropy number, it's something which I'm going to call measure of non-compactness. What is the geometric meaning of that? Geometric meaning of this is the following. If beta of T, measure of non-compactness, it's non-zero, it means that if I take a balls with the radius smaller than the value of this beta T, then it's impossible to cover image of unit ball by finitely many balls with such small radius, yes? If my radius is of covering balls is above this beta T, above this limit, then I can cover image of unit ball by finite number of balls with such radius, yes? Okay, which means this quantity it's called measure of non-compactness. Somehow this quantity it's absolutely same like limit of this. Yes, and now since those entropy numbers are in some sense behaving in some sense like those S numbers, which means first entropy number is always equal to the norm of our operator and then are decreasing, yes. Then it's always obvious that that beta t limit of those entropy numbers, that measure of non-compactness, must be always a non-negative number between 0 and norm of our operator t, yes. And I'm going to say here that for me, some operator it's maximally non-compact if it's true that the norm of that operator it's equal to the limit of entropy number. What does it mean? Operator is maximally non-compact if I want to cover the image of unit balls by sets slightly smaller than the diameter of that image, I will need to have infinite number of such balls. Yes, is maximum non-compact. Now there is a notion for measuring non-compactness by using some geometric criteria. Yes, there is also another concept used for measuring quality of non-compactness, and that is something which is called strictly singular maps. Yes, okay. What does it mean that some map between two Banach spaces is strictly singular? I'm going to say that the map T from one Banach space into another Banach space it's strictly singular if there is impossible to find infinitely dimensional closed subspace of our starting space X, on which restriction of T on that infinitely dimensional subspace, it's isomorphisms, which means what? It's invertible. Yes. If it's impossible to find such infinitely dimensional subspace, we are talking about strictly singular. Yes. In another way, we can say that some map it's strictly singular if for each infinitely dimensional closed subspace Z, this infimum is equal to 0, which means looking for the norm of T at X over the unit sphere, it's going to give you infimum 0, yes, for each infinite dimensional closed subspace, yes. Is a concept of strictly singular. Another concept which we need to mention here is something which is called finitely strictly singular. I'm going to mention that a map operator it's finitely strictly singular if there is information about behavior of the norm of Tx on subspaces with dimension greater than some given n. Yes, you will give me some big N, and if I will tell you that for each dimension or for each subspace with a dimension greater than n, there exists element for which norm is less than epsilon. If I have something like this, I'm going to say that my mapping is finitely strictly singular, yes, which means finitely strictly singular, it's somehow strictly singular mapping in which I have information about speed, how this quantity here goes to 0. This condition finitely strictly singular can be also written in the language of that so-called Bernstein numbers, yes? Which means if I knew that when I'm looking for the image of unit balls, and when I have information that in the image of unit ball, it's possible to put in the balls with the radius, with the dimension n, and then if I can see that with the increasing dimensions of that balls, radiuses might be smaller, this means that my embedding is finitely strictly singular, which means in another language, those Bernstein numbers are going to 0. Yes. Okay. Here we just introduce some notation you'll need in the next. And now here, of course, there's some relation. It's well known that if operator is compact, then it's finitely strictly singular, and that is a strictly singular. Yes. Okay. Now, this was just introduction and motivation. Now, what we will do in the next? In the next, we would like to try to look at the embedding between some function spaces defined on some open set omega. Yeah? And we have some embedding on function spaces defined on some open set. We can see that the non-compactness for such embeddings can happen from 3 different reasons. One reason is that our domain is unbounded. Another reason for non-compactness is that our domain is bounded, but boundary could be really bad and misbehaving. And the third reason for non-compactness is due to structure of your spaces, something from inside. Yes. And now the main thing you will study here is, of course, Sobolev embedding. Yes. When we are looking for the Sobolev embeddings, we all knew that if I'm consider this Sobolev embedding, omega here could be a nice bounded domain. The Sobolev embedding from Sobolev space WKP0 to space LQ, when k is integer, p is between 1 and infinity, kp between n, then this embedding is always compact when q is between 1 and up to this upper index. Yes. And I would like to look at this embedding and try to see when this embedding is non-compact and what's going to happen. I would like to start at first with one simple case. I would like to start for the case when domain is unbounded. Yes. This is started with the question which David Edmonds asked me about 10 years ago. And there was the following question. Let us suppose that we are just in 2-dimensional space, and I have a domain which is nothing other than just what? Just a pipe. Yes, just infinite pipe. And on this domain, I'm going to consider Sobolev embedding W1P0 into LP. Of course, this embedding was non-compact, and it was obvious that measure of non-compactness was positive. But there was a question, what should be exact value for that measure of non-compactness? Yes, I look at this with David Edmonds and Zdeněk Mihula, my collaborator, and we were able to obtain the following observation. We're able to obtain, of course, usually when we are solving problem, in order to solve it fast, it's sometimes a good idea to do it in the more general setup. Yes, instead of this problem here, we solve a little bit more general problem. We pick up some domain D, which was something like some n minus k dimensional rectangle, and it's going to be stretched in k dimension. Yes, we pick up this domain D. Yes, and on this domain we pick up this Sobolev norm. Yes, W1P0 was defined by this Sobolev norm, and we considered the Sobolev embedding. In this case, we were able to obtain exact values for measure of non-compactness, and also we were able to obtain exact value of norm. In this case, these two quantities were same, which means this Sobolev embedding was maximally non-compact. Yes, for P is this. Yes. Moreover, when we play with this, like a byproduct, we have some interesting results. What we obtain during the study of this, we were able to obtain the following. If I'm going to take this n-dimensional rectangle, and if I'm looking for extremal function on that n-dimensional rectangle with respect to this Rayleigh quotient, yes, then the extremal function for this quotient can be evaluated like a first eigenvalue of some pseudo P Laplacian. Yes, this equation, yes. Please, one thing, this is not a P Laplacian, it's pseudo P Laplacians. Why? We obtain this by taking pressure derivative of this expression, and there's a small norm LPS. We obtain this, and we were able to obtain what are the eigenfunctions. Eigenfunction for that corresponding eigenvalue is written in this language. By this byproduct, we solve some problem which Bernard Cavol asked, yes, about eigenfunction for P Laplacian, and moreover, we are able to produce that all functions of these forms must be eigenfunction of this pseudo P Laplacian problem. Yes, of course, we solve this, but there was one question left. We do not know if all eigenfunction for pseudo P Laplacian eigenvalue problems are of this form only, yes? Which means if there's any smart or curious graduate student looking for some project to do, this could be quite interesting project, yes? Which means this we did on unbounded region. Now we move on the situation when boundary, it's not nice, yes. It's obvious, one thing, when omega is bounded and has a good boundary, then this Sobolev embedding is always compact, yes. And we were asked the question if we can perturb domain in such way that our embedding will not be strictly single, which means our task was try to find here bad domain in such way that there will be infinitely dimensional subspace on which this Sobolev embedding will be almost identity, yes? And this we were able to find out with David Edmunds in our paper, which was published 2 years ago, yes? The main idea behind was the following. We just study behavior, of functions. Sorry for this, there's something hard to see as functions which are having what property? Function f which is constant here, and only this is increasing linearly, which means I have something like a stair. There's a landing, going up, landing, going up, landing, going up, and so on, yes? We look at the behavior of such function on this set, and by doing a simple undergrad level math, we were able to find what is gradient, what is LP norm of the gradient for that, what is LP norm of that function, we get ratio, and then just by gluing such regions to unit square, we were able to construct a sequence on which we were able to construct a domain on which it was possible to obtain a sequence of function fi's with the supports here, for which this identity was satisfied, and from that is following that this function will generate you infinitely dimensional subspace on which Sobolev embedding is invertible, yes? Okay. Now let us go and look for the third case, yes? Let us look here for something slightly more interesting than those two previous cases. Now my job was the following. Let us consider here Sobolev embedding, yes, which is going from Sobolev space VKP0, which is defined by this norm. We have here zero boundary condition into LP star. LP star is that highest possible index for which this Sobolev embedding is bounded. Important thing here. Omega, it's open. Pick up here LP space larger than this one, embedding is already compact. Yes. Now for this Sobolev embedding, it was proved by Hensel in 2003 that this embedding is maximally non-compact. Yes. But for Sobolev embeddings, LP star is not the optimal target space. It's possible to show that this Sobolev embedding, VKP0, it's going to be bounded into Lorentz spaces. Yes. And among all possible target spaces on which this Sobolev embedding is bounded, the possible smallest target space, it's Lorentz space of this form, LP star P. Yes. Which means we have boundedness of the Sobolev embedding into spaces LP star Q. Here Q goes, this is wrong, sorry, there should be typo. It should be going from P to Q, yes. In this case, that embedding is bounded, yes. In Buchala, it was proved that these embeddings were maximally non-compact, sorry, against typo. They should be Q, it's strictly larger or equal than P, strictly than infinity. And the remaining question was, what is going to happen in this concrete case? Yes. In this concrete case, when we look, and in some sense, this is quite interesting case, because this is, in some sense, the larger space in which this embedding is non-compact. If I'll take here significantly larger space, something like LP star minus epsilon, embedding will be already compact, yes. In this case, we study for this, yes. This is problem that somehow these spaces LP star infinity are spaces which are misbehaving. They are not having something which is called disjoint super additive property, which I used in the previous. What does it mean, disjoint super additive property? It means that somehow you can, if you will get a bunch of function with disjoint supports, then you can somehow get some chance to move some from outside to inside norm, yes. This is not true for infinity, yes. Nevertheless, in one of our paper, we were able to show that also this embedding was maximally non-compact, yes. Which means what we obtained was that this kind of Sobolev embeddings, it's always maximally non-compact embeddings, yes. In some sense, this is quite strange result. Why this is strange result? The reason for strangeness of this result is because here, when the Q is getting larger and larger, I'm getting here on the right-hand side larger and larger and larger spaces, which means embedding should be better and better behaving, should be more and more like a compact embedding. Nevertheless, the second index in Lorentz spaces does not have any impact, yes. It's still maximally non-compact, yes. This thing little bit puzzle us, yes. But we put these problems aside, and I look for the situation like this one. We look at the situation in which we pick up a Sobolev embedding, in which what? In which my derivatives were not like here in LP spaces, yes, but my derivatives were in some smaller space, L and K1 spaces, yes, this is smaller space. And we were able to see if your starting space, it's a Sobolev space with the kth level of smoothness, and your derivatives are in this Lorentz space, then the optimal target space is L infinity. Yes. Now, when we look at this embedding, by using some triangle coloring problem, we were able to obtain that in this case, our Sobolev embedding is not, it's maximally non-compact embedding. Yes, it was a little bit strange. In the previous case, optimal Sobolev embedding was maximally non-compact. He is not maximally non-compact. This forced us to go a little bit more closely on this embedding. And now what we did, let us just simply look at the situation when I have an embedding, which is just with the level of smoothness 1 here. So I'm not going to do here the smoothness in the level K or the K, but only level 1. In that case, I'm going to consider Sobolev embedding from LD1, from this Lorentz space. Derivatives are in this Lorentz space, and this is bounded into continuous function. And I look for the simple version only in 1 dimension, taking a Sobolev embedding from V1, 0, when my derivatives in L1 function and go to continuous function on the interval. Yes. Now, when we look at this embedding, by using zigzag theorem, which is really nice and interesting theorem, yes, it's worth it to mention it. Zigzag theorem, it's really nice theorem, which is going to tell me what? If I have n-dimensional subspace of continuous function on the bounded closed interval, then for each epsilon, there exists at least one function for my n-dimensional subspace, which has L infinite norm less than 1 plus epsilon, and that function is going to have at the end position changing values from 1 to -1, zigzag. Yes. Using this theorem, we were able to show that this Sobolev embedding will have Bernstein and isomorphism numbers going to 0, but the approximative numbers and Gelfand numbers are equal to half and Kolmogorov numbers equal to 1/4. Norm of this embedding is 1, yes, which means you can see from this it's not maximally non-compact, but Bernstein numbers are going to 0, which means this embedding is finitely strictly singular. Now, if we are trying to do this in the high dimension, there is one problem. If I have a cube in dimension D, I cannot put just line into cube. Or can I? Yes, I can try to use that zigzag theorem with the beauty of Hilbert curves, yes. With some technical results, we were able to use that zigzag theorem on Hilbert curves, and we were able to obtain that for Sobolev embeddings, Bernstein numbers are behaving like n to the power -12, which means they are going to 0, yes. Okay. Now, what we obtain from this? From this, we obtain that these Sobolev embeddings are finitely strictly singular, not maximally compact, yes. And now, now what we try to do? We try to see what we can do about those situations in which Sobolev embedding was maximally non-compact. Yes. Remember, we were able to find in the literature some result by Borgin and Gromov, in which they were able to show that this kind of Sobolev embedding is just going to have Bernstein numbers going to 0, yes. And nature question which we obtained from this and from the previous examples was what? Whether all those extremal Sobolev embeddings are finitely strictly singular or not. Answer to that question was no, but in some cases, yes. What we were able to obtain, we were able to prove that if I'm going to take a Sobolev embedding here from Sobolev space VMP0 into Lorentz space LP star P, this is the optimal target space. This is the smallest possible Banach function space in which these Sobolev functions are embedded. In that case, we were able to show that Bernstein numbers are always equal to 1. Moreover, we were able to show that this embedding was not strictly singular. There is infinitely dimensional subspace on which this embedding is almost identity. But if my target space is just going to be LP star, which means what? This is a space which is larger than this target space. In that case, we were able to show that the Bernstein numbers for this embedding was going to 0, which means this Sobolev embedding was finitely strictly singular, which means that we can see that these embeddings from previous are maximally non-compact, which means in the sense of entropy numbers, they are same, but there is a difference. This embedding is not strictly singular. This one is finitely strictly singular. And now what is now open problem is try to see what's going to happen between this space and this space, yes? Because this index P could be growing to P star, which means this space will be growing to this space. And we have no clue what's going to happen in that case. We cannot see if the P is replaced by something slightly larger and smaller than P star. We have no clue whether this embedding is strictly singular or not. Yes. And all these results were published in these papers. And I think that should be all what I want to mention. Now, are there any questions, comments, counterexamples? No? If there is any graduate student which is looking for nice, interesting project, it would be nice to see what's going to happen when the target spaces are laying between this Lorentz space and this space. What could be said or mentioned about quality of non-compactness in this case? Because in this case, it's not strictly single. There is infinite dimensions of space on which that mapping is almost identity. Nothing like that in this case. Okay.
Thank you for great presentation. It was very interesting.